My name is Peter Schlosser. I'm the Deputy Director and Director of Research of the US Institute, and I will introduce the moderator of today's session, Gavin Schmidt. Gavin is Deputy Chief and a Climate Scientist at the Goddard Institute for Space Studies of NASA, located just a little bit down Broadway here above Tom's Restaurant. He has been a frequent contributor to public communication on issues of climate. He also received for that activity the first Climate Communication Prize of the American Geophysical Union in 2011.
I'm going to talk a little bit about temperature changes over the last few years and years to come, why they change, what's going to happen to them in the future. What's going on? So this is a picture of the temperature anomalies for last year compared to a baseline back in the mid-20th century. Can we see that? Ooh, we can't really see that, can we? Oh, that's better. Yes. Okay, so double fisting the clickers here. So what we do when we're calculating these climate anomalies is that we take a picture of the climate from a period when we had a lot of information, say the mid-20th century, 1951 to 1980. We average the climate over that period, and then we judge whether, for instance, 2012 was warmer or colder than that particular period. So these colors up here are, if they're in the oranges and the reds, that means that they were warmer than this average by, the numbers here are around 2 degrees Celsius. So that's about just under 4 degrees Fahrenheit. This is 4 degrees, so the reds up here are around 7 odd degrees Fahrenheit, warmer than this average, right? So that's quite warm, and you'll see that almost everywhere on this map it's yellow and orange and red. So that means that on the whole, the planet has warmed since the 1950s, and that comes up in lots of different contexts. But it's not uniform, right? This is very important to know. If you just take the temperatures for a single year, it is actually, there are some places that are a little bit colder than the average. So down here in Antarctica, or, there's another little part of Antarctica that's colder. Alaska was a little bit colder last year than even in the 1950s. Right, but you'll remember that the continental US, this got a lot of headlines at the time, continental US had a record-breaking year, and I'll show you another graph that demonstrates that in a second. There's a couple of things to notice that happen, that occur in all these things. You'll notice that the land, this is Africa, South America, America, Europe. The land is more orange and red than the ocean, right? And that's something we expect. We expect that the land to be warming faster than the ocean, because basically the ocean has an enormous heat capacity. It takes a lot of energy to warm the ocean, much less to warm the land. And so as we move into a kind of globally warmed world, the land is expected to warm faster and to stay warmer longer. So this is kind of what it looked like in the annual mean. You see that there is structure. Not everywhere is warm. Some places are warmer than others. But overall, you can see that it was quite a warm year. If you just take a single month, right, you see a lot more structure because you're seeing a lot more weather. Right, so this is January, the last month for which we had data in this particular data set, and you can see that January was very warm in our part of the world. But there was, but California, Washington State was actually quite cold, and you can see there's a lot more structure, and that's because of the weather. That's because of where the storm systems were, where the jet stream was doing its thing, where the wiggles were, and so you get a sense that as you average over longer time periods, you lose some of that structure, right? So if you average over lots of different months which have different patterns, then you end up with a smoother pattern associated with the mean. If I average that over multiple years, I would end up with a smoother pattern still. If I look at the trends over 30 years, the pattern is smoother still. And so the noise associated with the weather goes down the more I average things in time and space. If you put it all together and you just get like one number for a single year, you end up with a picture like this. So this is the data that goes from the late 19th century up to 2012 is that last point there. And you can see that every year there's lots of ups and downs, right? That's an important part of what's going on. There's a lot of noise in that temperature. But then there's a very clear trend. If you average over a few years, you can see that back in the 19th century, it was kind of cool. There was a bit of a dip there. It warmed up to the 1940s. It was flat for a while, and then since around 1975, things have been moving upwards. But there's a lot of noise, right? There's a lot of ups and downs, and you shouldn't think that that's not important. That is important. And it's certainly important for how people perceive the changes that we've seen. It's also important to note what the scale is here, right? On the picture that we had before, the maximum numbers were 2, 4, 6 degrees, right? But when you average everything over the globe, the numbers, and this is with respect to the same baseline, the numbers are quite small. So they go from minus 0.4 to 0.6. That's a degree Celsius, roughly 2 degrees Fahrenheit in magnitude. Now, whether that's a big number or a small number really depends on the planet, right? It might be a very significant thing that's happened, but it might not have any practical consequences. Well, the fact is that it does have practical consequences. The parts of the planet that integrate over all the noise, the ice fields, the glaciers, the plants, the ecosystems, all of these things have reacted to these temperatures by the ice sheets. They're melting, the glaciers, they're melting, the plants, they're moving poleward and upward, trying to search for their kind of climatic niche, if you were. So this is a small number, but it's actually quite significant. And so here we are at the end, right? And you can see 2012, that wasn't a record-breaking year. You can see that this year was warmer, that was 2010. This year was warmer, 2005. And then there was this really kind of outlier year back in 1998. And we'll get to the reasons for why those were warmer than the others in a second. That was in the globe, right? So that's the whole globe averaged. But we can also look at different parts of the globe, right? So this is the northern latitude. So this is everything north of the tropics, and you can see that's a very similar pattern. Cool, warming to the 1940s, flattening, and then coming back up. And again, you can see that the noise is there. It's very clear, and you can see basically the same pattern. In the tropics themselves, you can see things have warmed in a more kind of linear fashion, if you like, but there's still a lot of noise. And if you actually look at the size of these anomalies, they're actually quite large. And I'll explain what these are about before as well, in a minute as well. And in the southern latitude, so this is everywhere south of the tropics, going down to the South Pole, the error bars here, these green lines, they're larger because we have less data from those kind of places. There's less land, there's less people. But you can see that that's been warming steadily as well. In fact, that's been warming, I think, more steadily than anywhere else. But the numbers are actually smaller. So the south has warmed less than the north, but there's a lot of noise in the tropics. And so all of these things need to be explained if you're going to try and understand how temperatures are changing year by year. We care particularly about the US, not because it's the most fundamentally important place in the climate, but it's the kind of fundamentally important place where we live, right? So that makes a difference. And you can see that, again, the scale here is bigger, right? So the noise that you're seeing, because this is a smaller region, is much larger, right? So, look at here in the northern latitudes, right? You've got about a degree point, in Celsius, you've got about 1.2 degrees from beginning to the end, and the noise level, maybe it's 0.4 in terms of the envelope there. If you look at the US temperature, which is about 4% of the northern hemisphere as a whole, right? Then the change is about the same. But the noise is much larger. If you look at the envelope of the noise, that's like 2 degrees. So the envelope of the noise in one particular location is much larger than the noise over the whole globe, right? And that's an important thing to bear in mind. Now, we said that last year the US had a particularly warm year. And you can see now, this is the 1930s, this is the time of the Dust Bowl, this is 1934, which was a particularly warm year, kind of right in the middle of that period, huge droughts in that time period as well. And you can see kind of the temperatures fell, and then, since again, around 1970, they've started to rise up again. And so this is 2011, here this is 2012. Right, so 2012, we had to extend the graph, right, because we had to change the axes because it was so far off the scale. Now, does it mean that we're going to be up there forever? No. I mean, next year it's very likely. If you look at all the ups and downs, it's very likely that it's going to be colder than that. Right? Does that mean that global warming has stopped? No, it doesn't. It just means that there's a lot of noise that adds to the long-term trends, and that's what makes the record. So. Okay. So how does the media report these things? So this is in the Daily Mail. The media reports these things by taking a tiny little fraction of that record. So they picked a period here from August 1997 to August 2012 and made it seem like there's nothing happening at all. There's nothing happening at all. See? And the Met Office, this is Met Office data from the UK, and the Met Office saying that global warming has stopped. Canada is not immune from silliness. And they use graphs like this. So, by putting the 0 point, look, nothing has happened. Nothing has happened at all. So, interestingly enough, this kind of scaling is equivalent to trying to hide a 60-foot sea level rise by using the total depth of the ocean. Right? Because 60-foot in sea level rise, well, that's not going to bother anybody, is it? No, look how small it is in the percentage terms. Of course, in temperature, this is completely arbitrary. And if they'd done it in Fahrenheit, it would have been completely different. So they can make up their own thing. So this is people who are trying to hide something from you, and judging by their comment sections, they are actually managing to hide it from quite a lot of people. But the fact of the matter is that these are not fair depictions of what's going on. Right? If we can examine that a little bit further, this is a graph I made based on what they did there. There's a lot here. I'm going to walk you through it. So this is that same data, right? And this is the data that they plotted. Just from this line here to there, right? So the fact that they're ignoring all of this stuff. This goes back to 1975, and the rest of it, you know what it looks like, right? This is the bit that they plotted, right? This blue line. So that's the blue line. That's the trend from this particular period to that particular period. Now, the reason why they picked that particular period is because that was the flattest they could make it, so it's not like, oh, well, this is a particularly important thing that the trend from August 1997 should be important. They just picked August 1997 because that gave us the flattest line, right? If they'd picked a time a little later, then it would have been nicely positive. If they put the time a little earlier, it would have been nicely positive. But that's not the message they wanted to show. And so, your people are. It's what's called cherry picking. You're picking different pieces of the fruit.
But might someone say that about time scale we've chosen as well?
Yes, you can say that indeed. My point is going to be a slightly different one. So you can pick this and you can put these lines, calculating these straight lines through a set of points is a standard mathematical thing, and you can calculate what the number is. There's no mystery here. But what you're doing is you're basically looking at noise, right? So you're looking at the day-to-day fluctuations on Wall Street instead of the long-term growth records of any particular stock or something like that. Now, it was quite interesting that they picked that period. Because if you take the trends, say from 1975, which is the beginning of that warming period, to July 1997, right, which is just before they started this thing, then you would have ended up with this green line. And then if you said, okay, well, if that was the trend that we thought was happening up until then, and we just extended it forward to August 2012, it got August 2012 right to 3 decimal places, which is pretty amazing, actually. 0.524 degrees Celsius was the estimate, and 0.523 degrees was the actual number, which obviously is just coincidence. But it does tell you that, if you'd done that, if you'd extended that line out, you'd have actually had a pretty good estimate of what was going on. Curiously enough, if you take the trend over that whole period, right, the trend has actually increased because you've had, basically periods that are permanently warm, right? We've moved into a new permanently warm plateau, if you like. So the longer this goes on, the longer the higher these trends are going to get. And so that's actually greater. So it's odd that they claim that there's been no warming since then, but actually this has actually increased the warming since before then. It's kind of contradictory. It just means that there's not any magic in the mathematics. It's just that this kind of mathematics is not very good at making predictions, right? Putting straight lines through things, put a straight line through, I don't know, think of something, and then extrapolate it forever. It's not generally a good idea. More kind of robustly, you can look at things like decadal means, right? So I said earlier on that the longer the period that you average over and the bigger the area that you average over, the stronger the signal becomes, right? And so if you look at the decadal means, which are these purple lines here, right? That was the 1980s, that's the 1990s, the 2000s, the last 10 years. And you can see that every 10 years, like, we're kind of moving up. And that's a very strong signal. And that's really what we're talking about when we're talking about global warming. We're not talking about, whether it's cooled or warmed since last Tuesday. We're talking about what the long-term trend is in the temperature. Now, we talk about that because we think we understand why that is. Now, we understand some of these ups and downs too, and I'll go into that. But basically, the reason why we're warming at a steady pace in the decadal means is because we're adding greenhouse gases to the atmosphere, and prominent among those is carbon dioxide. The key thing here is that you can find trends. In fact, you can find negative trends in the whole time series, and you just join them up one after the other, and every trend is negative, but of course the whole trend is positive. And there's a great, I should have brought that out. There's a great GIF animation on skeptical science called the skeptic elevator, where you just go through the time series and they show negative trend, negative trend, negative trend, but all the time at a higher and higher level, and that's how some people in the media see the temperature change. So what is actually going on in these short-term cases? And there's some very interesting physics there, and I recommend that you kind of look into it. And the biggest impact on this is what's called the El Nino-La Nina oscillation or phenomena. And I'm sure Richard will mention this a little bit later on as well. This is a phenomena that's mostly kind of that's kind of a big deal in the Pacific. And so what I picked here is this is the difference between 2011, which was a La Nina year, and 1998, which was a big El Nino year, right? And you can see the difference. So 2011 was a little bit colder than 1998. But you can see where that temperature change is coming from. It's coming from this big patch of cooling in the tropical Pacific. And this is a very familiar pattern to people who look at these things. So you've got this big cooling right on the equator, and then you've got this kind of horseshoe of warm temperatures around it. And this is very reminiscent of this La Nina pattern. And an El Nino pattern, you can think of it as just the flip of that. So in an El Nino, this area would be warm and this area would be cool. And this is such a large and important part of the planet's climate that it actually has an impact on the global temperature. Right? You can see every year when there's an El Nino, you're a little bit warmer. Every year when there's a La Nina, you're a little bit cooler. There's a little bit of a lag as all the bits kind of come into place. But a lot of that ups and downs, all of those ups and downs that you see, they're associated with this El Nino-La Nina phenomenon. And so 2011 was a La Nina, relatively cold. 1998 was an El Nino, relatively hot. Right? So, so we can quantify that. There's what's called an ENSO index, which is the El Nino Southern Oscillation, and that basically takes a sea surface temperature average in this region here, and when that's negative, then you've got a La Nina, and when it's positive, you have an El Nino. Right? And that gives us a kind of independent estimate of when these particular phenomena are going on. What happens, the dynamics of this is fascinating. So what happens is you have kind of waves that go across the Pacific that kind of push the clouds and the convection from one end to the other. This is normally where everything is going on. It kind of, in an El Nino, it kind of moves further towards South America. In a La Nina, it moves further towards Australia and Indonesia. And everything changes. Rainfall patterns change, waves change, temperatures change. It's a really big deal. So what you can do is you can say, okay, well, I understand a little bit about how the temperatures change as a function of El Nino or La Nina, and I can take that away. Right? I'm going to just adjust the temperatures so that I'm going to try and take away the influence of that, and then you end up with a picture like this, right? So if you remember the global mean temperature, there was a lot more ups and downs. But like when you take away the El Nino effect, what you end up with, and this is 5 different estimates of the global surface mean temperature, you can see that the amount of ups and downs is much less, and then you end up with a trend that continues all the way up to 2012. So there's no if you go to like 1997, which is when that graphic was talking about. So this is 95, 96, so 97. So there's a very clear long-term trend that is subsequent to 1997. And that's because what's happened is the last few years we've had a couple of really big La Ninas, which in 2010 was a big La Nina, the end of 2010, and then in 2012 there was a kind of semi-La Nina. And then this year we're going into ENSO neutral conditions. So it's kind of neither one thing nor the other. And I'll show you what that implication that has in a second. And so when you look at that data, again, apologize, there's a lot of information here. So again, this is the temperature, right? So, but the temperatures aren't all joined up like they were before, right? So here, this would be the temperature that you actually saw if you joined up all the lines, right? There's that 1998 point again, right? There's that 2011 point. It's the same data, but what they've done here is they've stratified it by whether there was an El Nino condition or a La Nina condition or something in the middle. So if you draw a line through all the El Ninos, right, which are all warmer than average, you get this warm trend that's going up. If you put a line through all the La Ninas, you also get a trend that's going up, and you'll notice that the trends are the same, right? So what's happening is that you've got noise, El Nino, La Nina, El Nino, La Nina, but then you've got a baseline that's moving, right? And that baseline is moving up, and that's that forced signal. That's the signal that's being driven by human activities for the most part. And so you can actually, based on that, you can make a prediction for where 2013 is going to end up. We haven't really started 2013 yet in this kind of thing, so this is a real prediction. And since we're in an ENSO neutral state, that's this yellow line, what we're estimating, well, this is an estimate from the state climatologist of Texas. So that's important. And he's estimating that this is where you would end up with 2013. And actually, it's very interesting. If you look at it, he's actually predicting that this is going to be the warmest year on record, right? Just based on what the phase of ENSO is in the last few months. So if that comes out, obviously there's some, if it's here, then it won't be. But if it's here, it'll be a really big deal. It seems likely, then, that we will see a new record this year. It won't stop people pretending that global warming stopped 16 years ago, but it's a little bit odd that global warming stops and yet there's still so many records being broken. I wonder why that is. It's when we go forward for further times, what we need are models, and the models that we use are what are called general circulation models. They're big, they're complicated, lots of lines of Fortran code. Some of you old timers might know what that is. And every so often we get together, all the modeling groups, and we make predictions for what's going to happen if carbon dioxide continues to increase or something else is going to change. We did that a while ago in what was called CMIP3, and that was done in the early 2000s. And so what people did was they used observational data for the sun and volcanoes and greenhouse gases up to the year 2000, and they ran their models. And then after the year 2000, they said, okay, well, where's carbon dioxide? Where do we think that's going to go? We made some prediction about that. And so all of these, everything that's in these gray bars are all these different model runs. There's about 57 different model runs that went into making this particular plot. And this gray bar is a measure of the weather, essentially. It's saying that, well, some models, when they got to here, they had an El Nino, and they'd be up there. And some models, when they got there, they'd have a La Nina, because that's part of the noise. It's part of the internal variability. And so this spread is pretty much what you expect, just based on the uncertainty in the weather, and the fact that we don't know where we are in insospace, if you like. There's a couple of big dips. There's a dip here in the 1990s, 1991, in fact, and that was because there was a big volcano. And when there's a big volcano that throws up a lot of stuff into the atmosphere, that cools the planet because that provides a shielding to solar radiation. There was another volcano here in the 1980s, El Chichon. But apart from that, what you're looking at here is a slow trend because of the increase in greenhouse gases, combined with noise associated with ENSO and La Nina and the like. So this was 1998. That was a warm year in the real world, but the models don't know anything about that, so they don't always have a big point here. But they have a spread. And then from here on in, from 2000 onwards, what you have is the predictions essentially. Now, the carbon dioxide changes have been pretty much what we expected. There have been a couple of small volcanoes. There's been some change in the sun that wasn't properly taken into account. But basically, this is what we expect the real world to be doing. And this is the average of all those models. So that's averaging over all of that weather. So that's not a really fair comparison to just make with one particular realization of the real world. But here we go, there's 2012. And so what you can see is that the real world is pretty much well within the band of what we predicted. And this goes on, and can you see the dot? It goes on, ends up over there somewhere. If we continue on a business as usual trajectory, which we don't see any sign that we're not going to do right yet. And what we anticipate is that the real world will, basically follow that. If Nielsen-Gammon's prediction is correct, 2013 will be up here, and then it will just be kind of obvious that the real world is actually following what the models predicted they would actually do. And this is important because this is an out of sample test, right? We didn't know what this data was going to be before we did the models, right? So they're real predictions that can be tested in time. So let me conclude, and then I'm going to turn it over to our other guys. Global warming, the long-term trend in temperatures that we've seen since the 19th century, and most recently since the 1970s, has been remarkably steady. Once you take account of all the ups and downs and the noise in the system and the things that have nothing to do with us, it's been continuing for a long while. There's no indication that we can tell that global warming has stopped or slowed. If you look at other metrics, like the amount of heat going into the ocean, that's increasing continuously. If you look at other metrics like the Arctic sea ice, that is decreasing pretty much continuously. There's noise, but our ongoing experiment, our ongoing geophysical experiment is continuing. The short-term variability is really strongly affected by ENSO, by El Nino, by internal variability, by where the jet stream is this particular winter time. And you have to take that into account. You have to look through that to see what the long-term trends is. If people spend a lot of time just looking at the weather, then it's kind of like you're not seeing the forest for the trees. One of the ways to get around that is to look at these kind of long-term means, like every 10 years, how are things changing? And every 10 years, we're in a warmer place. And in the next 10 years, we'll be in a warmer place still. Because we're in an ENSO neutral phase, so neither La Nina or El Nino, 2013 looks like it's going to be a new record. Now, this is being recorded, right? So I'm just going to say very clearly, it's not my prediction. It was the other guy, but it's it is a reasonable and it's a reasonable way of predicting things. And then, of course, the biggest thing you should always bear in mind is don't believe anything you read in the newspapers, particularly not the Daily Mail or the National Post. Okay, so with that, I'm going to turn it over to Richard. I'll be happy to answer any questions while we're just doing a little bit of technical messing around here. Oh, you got it first? Okay, yes. Okay, then Jason. Yes. Okay, so, yes.
Why is that aluminum phenomenon so important? Why is that area of the world so critical for the global impact?
So that's a great question. So the tropics are the warmest part of the planet. The tropics are the warmest part of the planet, and that's where most of the deep convection happens. You know, these big towering cumulus clouds that you see, tropical downpours. And most of that is centered in the western Pacific, right? So around Indonesia, Borneo, north of the northern part of Australia. That's the western Pacific warm pool. That is probably the key player in global climate. It sets up how much water vapor is in the air. It sets up where the Hadley cell is. It sets up the circulation that determines where you're going to have a wet area and where you're going to have a dry area. It's a really key part of the planet. And an El Nino is a perturbation to that really key thing, right? So that area of convection, which is normally over the western Pacific, it can move, right? And there's a couple of very interesting kinds of dynamics that are happening in the atmosphere and in the ocean that cause that to move. So it's a coupled thing. It doesn't happen when you just have an ocean. It doesn't happen when you just look at the atmosphere. But it's a coupled it's a coupled phenomena, and that can move, and it has this kind of like 3 to 5 year periodicity, and it can move a little bit further towards South America, and it can move a little bit further away from South America. And that is, it makes a huge impact on rainfall patterns in Indonesia. In an El Nino, Indonesia is in drought, Australia is in drought, but the rain in Peru is huge, right? So El Nino comes from the Spanish fishermen in Peru who first noticed this phenomena, and they would say, okay, well, there's years when we're not catching any fish, and then there's years when we're catching lots of fish, and it would come in at Christmas time, and so it kind of came with the Christ child. So El Nino. When scientists started looking at this, and they said, okay, well, look, there's a positive thing, which is this El Nino, and then there's this negative thing. What should we call it? And for a while there, a few people tried to call it the anti-El Nino, but then like the Antichrist really didn't translate very well, so that got tossed, and so now we call it La Nina, the girl child, right? So, but it's a really crucial part of the system.
About how the links between climate and hydrological extremes, in particular drought. As you all know, we are now in year 3 of a pretty serious drought within North America, within the United States, but also in Mexico. The map on the upper right is the US drought monitor for last week. Those maps come out every Thursday, so the next one comes out at 9 o'clock tomorrow morning from the Department of Agriculture, NOAA, and various other federal agencies. And then the North American drought monitor, which includes information from Canada and Mexico, only comes out once a month, and the February map is the one there on the top left. So what you can see is that although we've come through a winter and we're heading off into spring and summer, the United States, and to a lesser extent Mexico, is already in an extraordinarily severe drought situation. I don't know how many of you have actually been out west. Recently I was out there in February in Colorado, and I'd never seen this in the United States before, but you actually saw cattle and horses starving in the fields with their ribs sticking out, looking like pictures you see of cattle and livestock in Africa, just because there's nothing for them to eat. Hay prices are too high for farmers to buy feed for animals. And taking a longer-term perspective, the picture on the bottom right is the elevation of Lake Powell, which was one of the 2 big reservoirs along the Colorado River, which is the water, the lifeblood of the southwestern United States and to some extent Mexico as well. That reservoir was built in the 1960s, so it's filled up in the 1960s. It did fairly well for quite a while, and then after that famous 97-98 El Nino that Gavin mentioned, we went through a climate regime shift, which has been overall drier in the southwestern United States, and the reservoir right now is down something like 60% full. It did get down to much lower than that in 2002. So there's long-term water supply shortages within the southwest. Okay, so what has actually been has caused us to go into such a situation? The drought, of course, features also as one of these multi-billion-dollar climate disasters that Jason mentioned. Crop damage, the agricultural cost of crop failure to the federal taxpayer, to us, of last year is in the sort of the $30 billion range right now. There's a lot of additional costs due to the drought, but it's combined with all the other costs of last year, it's helping make 2012 and then 2011 before it really records in terms of costs of climate weather-related disasters in the United States. But if we actually go back to summer of 2010, for about the first time in 10 years, there was almost no drought anywhere within the United States or North America, a few patches here and there. But then what happened is that a La Nina developed in the tropical Pacific Ocean, and these just occur from natural interactions between the tropical Pacific atmosphere and ocean, and it's an endless ongoing cycle, as Gavin pointed out. And in the winter of 2010 to 2011, a very strong La Nina developed. That's the sea surface temperature anomaly there. Sorry, I missed the scale, but it's about a -2, -3 degrees centigrade anomaly. Whenever this happens, it sets up a load of changes in atmospheric circulation that affect weather all over the world. And in North America, in mid-latitude North America as well as mid-latitude South America, it causes drought. It does various things in other parts of the world. So, not surprisingly, since this developed in winter of 2010-11, by the time you got round to spring of 2011, you had a drought in the southern part of the United States and northern Mexico that was already looking pretty severe. And this was actually predicted well in advance. I remember actually giving a talk to the Western Governors Association in September of 2010, when they were very happy looking at this map and saying, because operational forecast agencies were predicting that a La Nina of good strength would develop that winter, we were also predicting that a drought would develop. And the drought that was predicted was not as severe as the one that developed, but moving the United States and northern Mexico back into drought was well predicted months in advance. And then as it went on, that La Nina continued all the way through until spring of last year. So this is actually a sea surface temperature averaged over all of spring 2011 to 2012. There's the cold tropical Pacific Ocean. And by the time you got into spring of last year, that drought had now spread over into the southwest of California. It has stayed there in Texas and Mexico, southeast, so it's already causing a lot of trouble. And then a rather interesting thing happened, because the La Nina went away, was replaced with warm waters in the tropical Pacific in summer of last year. However, the drought both intensified and extended remarkably rapidly up into the Midwest. In spring of 2012, there was almost no drought in the Midwest of the United States. By the summer of 2012, most of those regions were in extreme to exceptional drought. We have no ability to predict summer hydroclimate extremes in the United States whatsoever. So going from this drought monitor map to that drought monitor map was entirely unpredicted by every forecasting agency within the world. And to the extent that the oceans actually went to a El Nino, you might have thought that it might have been a little wetter in this region in summer of 2012, but it wasn't. So there's probably this intensification of the drought that happened here happened to be some random atmospheric event, circulation anomaly that was added on, that came on the tail of an ocean-forced drought that had lasted for 2 years up to then. Okay. So if we look at then this in terms of a longer term perspective, this is actually going from 1950 to 2011, and its precipitation and temperature averaged over Texas, the southern plains really, Texas and northern Mexico, and it's just for the summers, and its precipitation, which is the line. So first of all, there's the summer of 2011, and if 2012 was on here as well, it would be just as extreme or more extreme, and you can see that that was really setting a record since 1950 in terms of dryness. And then the air temperature is on here as well. Actually, the air temperature is the bar and the precipitation is the line. But the temperature is being turned upside down, so consequently you can see that there's a very strong inverse relationship between these. When it gets the high temperatures that occurred in Texas, in the plains during this 2-year drought were because it was so dry. When the soil gets that dry, the surface has to cool by radiation or sensible heat flux, and it gets very hot. It's like comparing a car park to the lawn next door to it when they have the same amount of sun coming in. A bare land surface, a bare dry land surface warms up a lot more. So the record temperatures were really explained in this region by the record dryness that occurred at the same time. So it's the drought that caused the high temperatures. If you look at the long-term trend, there's neither a trend in Texas in temperature or precipitation. It really has, it's not getting drier there, it's not getting hotter there. This is one of the few places in the world which hasn't actually warmed up over the 20th century, Texas. So pretty much I think in order to explain the extreme event that we are still going through within the drought in the United States, it is, just go back, it is almost entirely caused by just the natural variability of the atmosphere and ocean system. The record-breaking temperatures themselves probably do get a little bit of an add-on effect from like there being some background global warming, but even they are primarily due to this natural variability going on. Which is not to say that hydrological changes due to how we are changing the composition of the atmosphere are not important. They actually are, of course, very important as well. And this is roughly what we expect to happen. Greenhouse warming will impact patterns of precipitation, less evaporation. So that's that's the quantity that we tend to use for this, because it's the net flux of water at the surface of the Earth. And it'll impact these patterns across the planet. Right now, this is model simulations of the P-E distribution that we have in the 20th century, and we have positive values near the equator, so precipitations in excess of evaporation where you have very strong tropical rain bands, and also in mid-latitudes like where we are, we have excess of precipitation over evaporation. And then in the subtropics, where all your deserts are, you have negative values of this. In other words, the precipitation is less than the evaporation. These are all the places where where there's very little precipitation. And the reason there is that distribution is because the atmosphere moves moisture around. So the arrows here are low-level winds, and you can see wherever the winds, here they are, the trade winds, wherever they converge, they bring moisture there, it rains a lot, the precipitation exceeds the evaporation. And in these subtropical regions, you can see they lie in between the trades flowing towards the equator and westerlies flowing away from the subtropics. So these are regions of moisture divergence, and they tend to be dry. What happens when you increase the temperature of the air due to increase in greenhouse gases, the air, through pure thermodynamics, can hold more moisture. So consequently, this movement of moisture by the winds in the atmosphere intensifies. And that just makes the hydrological variations more extreme. So it makes the dry areas drier, and it makes the wet areas wetter. So you can see how well the change in P-E in these model simulations for the next 2 decades relative to the late 20th century, you can see how well that change maps onto the existing distribution, where places that were already wet get wetter, and places that were already dry, including Mexico, southwest US, Mediterranean region, get drier as well. And it's a little harder to see on the picture there, but in addition to extremes getting more extreme in place, you actually find that these subtropical dry zones expand. They both expand towards the equator and they expand towards the higher latitudes as well. And that's because there are some additional changes in atmospheric circulation that increasing greenhouse gases cause too. Looking at that over North America, this is what the models predicted the last time we did this in 2007 with the models that we used for the IPCC Assessment Report 4. This is what the models which are being used for IPCC Assessment Report 5, which will be published next year or in 2015, are producing. So after years and years more of running computer models of vast complexity and sucking up much of the world's computing resources, we've come back to exactly the same result. That didn't really change that very much, but you can see that for winter half years and summer half years, the southwestern part of the United States, including Texas, Mexico, gets drier, and in the summer part of the half year, that drying is mostly over the central to northern parts of the United States, including the major agricultural producing region there within the Midwest. This is almost certainly going to have some fairly serious impacts on agriculture, water resources, and of course the landscape in the ecosystem, natural ecosystems, forests and so on are going to have to adapt to this, which is going to be quite a problem for, say, southwestern forests. Okay, in the most recent simulations, you can do things like try to compute what it means, say, for the runoff of the Colorado River, and we have done that. And this is this is the boxes here. It's percent change in Colorado River runoff by season and by the annual mean, and the spread of all the different models. There was something like 20-something climate models that were analyzed in this, multiple runs of different models, so you get different numbers depending on all of those, but they seem to come out that in the annual mean there's about, the best estimate would be about a 10% reduction in Colorado River runoff. This is actually for 2021 to 2040. And you can compare that with long tree ring-based reconstructions of Colorado River flow that we have that go back to 800. And there were a whole load of mega droughts that occurred in the medieval period that we know had very, very serious impacts on the landscape at the time. And those droughts themselves were also about 10-15% reductions, were associated with 10-15% reductions in Colorado river flow. So the anthropogenic change that is being induced in the river flow within the next 2-decade period, so that's really the near-term future, is of the same amplitude as what can happen due to natural variability of the climate system on multi-decadal timescales. The difference, of course, is that when the natural climate system does this, it does it for a few decades and then stops and does something else. But what the humans are doing to the climate change, this is induced by rising greenhouse gases, this 10% reduction, and it will go on as long as we keep the CO2 up in the atmosphere. So it's a permanent change, it's that permanence that means that it's something unlike what we would ever see before, and the whole landscape and ecosystem of this region is going to have to make some rather drastic adjustment to that increasing aridity. But nonetheless, if you go back to what I said about the ongoing Texas drought, the natural variability in the southwest of the US is so large that it's hard to clearly detect that change is already happening. And we've tried to detect whether these changes are happening in other regions of the world as well, in Africa, South America, and so on. And it's the climate variability is of such high amplitude that it's generally rather difficult to find, although we do think that these human-induced changes are occurring. But there is one region in the world where it seems almost unambiguous that human-induced hydrological change is already occurring, and that's the Mediterranean. The latter part of the 20th century had a rather serious drying across the entire Mediterranean region. This has been reversed in much of the Mediterranean in recent years, but not in the Middle East region. And we've done some work where we try to separate out that trend into a part that is due to natural variability, and that part is largely controlled by an atmospheric circulation phenomenon called the North Atlantic Oscillation, which some of you may have heard of, which has impressively long ability to vary on decade timescales, and it went through its own trend. Within the late 1990s, it trended towards a positive state, which moves the storm tracks over the North Atlantic and so on, and however it works, it makes the Mediterranean dry. And much of this trend that occurred was due to this just trend in the natural trend due to natural variability of the North Atlantic Oscillation. But we were unable to explain the drying that occurred in the Middle Eastern region and to some extent over in Morocco and southern Spain due to that trend in the natural variability of the atmosphere. And instead, this part in the Middle East we could only explain in terms of a rise in greenhouse gases. And it was although this was an entirely observational analysis, climate models predict that this region should have been getting drier and will continue to get drier. And while we focused on this very strong drying trend with this period, if you extend this analysis up to 2012, you still get the Middle Eastern region drying can only be explained in terms of rising greenhouse gases. That has proven to be highly important in recent years because it seems to have been implicated in some of the unrest there in Syria with agricultural collapse in the regions of northern Syria induced by this drought. And a couple of think tanks prepared a big report about that they released last week. And that may well turn out to be a case where climate change, human-induced climate change, is clearly translating through to social revolution. Okay, just one other thing to think about, which is what I was talking there was changes in mean precipitation. Climate change also impacts precipitation extremes. So this is a plot by latitude of the amount of precipitation that occurs in the heaviest 0.1% of events. So one of these lines here is observations of that, and the other one is climate model simulations of the late 20th century. And then the red one here is a simulation of the same quantity at the end of the 21st century. So the climate models predict that pretty much everywhere the heaviest 1% of precipitation events will have significantly more rainfall within them than they did in the 20th century. This has actually been observed over a lot of places, and including in the United States, from rain gauge records, where this is a time series from 1900 to 2000 or so of the amount of the precipitation within the heaviest 1% of events or the heaviest 0.1% of events, and you see it moves along and then it jumps up in the late 20th century. And the same scientists have done this analysis in other parts of the world and found that this is an observed change, that more of our rainfall is falling in the very heaviest precipitation events, separated out by longer dry spells in between. And the explanation for this is really the same as the explanation for the mean change in the hydrological cycle, which is the water vapor in the atmosphere goes up. When the water vapor in the atmosphere goes up, any existing storm system can draw on more moisture, and it can rain out more moisture when atmospheric conditions are prone to producing precipitation. So you just put more moisture in the atmosphere, you are going to get more of these extreme precipitation events. This is a map of the change in lower level moisture in percent. It's like 14, 15, 20%. And this is for the early 21st century, and then this is actually a map of the change in the variance of P-E, annual mean variance in this case, and you can see that goes up pretty much everywhere, apart from some of those regions where the mean precipitation is going to go down, including the southwest US and Mexico, where it seems actually variance will go down because actually the mean precipitation is going down and there isn't that much of an increase there isn't such a high increase in moisture within those regions. Okay, so to conclude, any extreme events that happen, they almost always arise from natural climate variability. So, for example, North American droughts that are produced by La Nina events or atmospheric blocking events that cause intense drying heat. The summer heat wave in 2003 in Europe would be one of those, or March, if you remember last year we had 20 degrees temperature anomalies in Chicago and the Midwest. That again was due to a blocking event, which is all due to natural climate variability. But the way that the climate change comes in is that when you have these extremes that come about from natural variability, climate change can make those extremes become even more extreme. So if you're in a region where climate change is causing drier conditions to emerge, droughts will just become more severe. And when you have wet times, they won't be as wet as they would be. In addition, rising temperatures, by increasing the atmospheric water vapor holding capacity, sucking more moisture out of soils and out of vegetation, and reducing soil moisture and stream flow. That's just going to be happening everywhere. So you have the rising temperatures creating water stress, even if you aren't even if you're not in a place where the precipitation is going to go down. And then the other consequence of rising atmospheric humidity, which is just a consequence of warming, is that it will always intensify water vapor transport. Now, anywhere where it rains, it's because moisture is being moved into that region by the atmosphere. So you're always going to be moving more moisture in because the atmosphere is holding more, and that can increase extremes of precipitation on all time scales, on the hourly time scale, the daily time scale, the annual mean time scale. This just occurs on all time scales. Okay, thank you.
Summarizing some of these observations and extreme events, because at the end of the day, I'm just one schmuck who's standing up here and talking to you about things from my perspective. But what this really represents is a collective synthesis of the science as it stands every 5 to 7 years. And I think it's worth reading these statements because it really does represent a wide consensus on what we know about extremes and what we understand about them. So this is their statement in 2007. There'll be a new report coming out next year, but this is the synthesis as it stood in 2007. So if we take a global view of this, there's different ways that this can be mapped. Now, Gavin has already shown you anomalies. So this is, again, are those spatial maps of anomalies, but in this case it's just June, July, August temperatures, all right, with a base period of 1951 to 1980. And what these maps are doing is stepping through the years. This is 1955, 65, 75, and then these are the last several years. So it's 06, 07, 08, 09, 2010, and 2011. And what is being plotted is the temperature anomalies relative to that base period. And if you just look at the way this is going, you're of course seeing many more red periods representing the warmer periods on these scales. These are things that you would not expect to see without a shift in the distribution. If we just assume that historical distribution, these are events, warming events at all these locations that you would not expect to be seeing otherwise. Estimates of how we expect things to change into the future. So these are the distributions for the first, from 2020 to 2029, and then the distribution at the end of the 21st century in the global mean for different scenarios. All right, so these scenarios represent different assumptions about the choices we're going to make as societies, how much greenhouse, how we're going to change our mix of energy and so on. But what they all show is if you accept this as an initial distribution within the century, this increase in the mean, and also a tendency towards warmer events later, higher up on the distribution.